Alright, for the second part of this video, we are going to see how you can graph. So let's get started. So I do apologize for not fitting it in. So Diana is studying the relation between the length of a spring when masses or lap weights are attached. She experimented and recorded data in the following table. Draw a linear graph to show the relation. So let's look at the table for a second. This is what she's changing, and this is how the spring is changing. So this is the independent variable, and this is the dependent variable. So a table has to have titles, obviously, or labels. Look at that. It has units, and this is going to make your job easier when you're doing your own graphs. Let's focus on 0 for a minute. 0, mass 8 centimeters. That means that you started with no weights, and the original spring was 8 centimeters long. Then you added 1 kilogram, and it went to 10 centimeters. Then 2 went to 12. And 3 went to 14. So with this information, we are going to graphs. So I can cheat a little bit. Let's use the technology. Here I have a graph, a number plane, and as you can see, I've already put a title, length of the spring when mass is attached. Here's my dependent variable, spring length, and there's my unit, and I label it. And here is my independent variable, mass and kilograms. So let's put these numbers into our table. So let's start with 0. So when she started with no mass, the spring was originally 8 centimeters long. So there's our first point. Then she added 1 kilogram, and the spring went to 10 centimeters. Then she did 2, and the spring went to 12. And lastly, she put 3 kilograms, and the spring went to 14. So you can see these points already lining up very neatly. So what you can do, I'll take a different color pen and a ruler, and let's join those points. So there we go. Now I'm going to go a step further, and I'm going to extrapolate this line. That is, I'm going to extend it, because if it works for the first 4, we could predict that it will stay and it will follow the same pattern all the way through. So there is our first line. We can now answer some questions. How long will the spring be if attaches 1.5 kilograms to the spring? So we can look at the information here. It says if we attach 1.5, what will we get? So let's go to our mass. 1.5 is between 1 and 2, halfway. So we can assume that's 1.5 there. We can use a ruler to draw a line up until you meet the line that we just drawn, and then we can read across. And according to this, if you attach 1.5 kilograms to your spring, you should get a length of 11 centimeters. So we can answer the question 11 centimeters. Next one, someone misplaced the 11 kilogram mass. Use the graph to tell Dana how long the spring will be. So In the first question, we had points in between. But look at 11. 11 is a bit off. But this is where extending the line makes it very useful. We call that extrapolate. So we can make a prediction. You don't have to be right. It's just a prediction. We go 11 kilograms. We go draw all the way up. And then we can read across. So we get 30. So it seems that if you were to attach an 11 kilogram to this spring, you will get a spring length of 30 centimeters. Good. All right. Next one, Harry stated his sprint speed over a distance of 20 meters. He asked two friends to record his time every 10 meters. With this data, Harry decides to plot a distance time line graph, and here's his data. So obviously at 0 distance, that's his starting point, so that's his starting time. It took him 2.5 seconds to do 10 meters, and it took him 4.5 seconds to do the 20 meters. So here's my graph again. Harry's sprint time, and here my distance and my time, my labels with the corresponding units. Now, we don't have exact time, so 1, 2, 3, 4. We only have decimal time, so let's get started. So first of all, we have the point 0, 0. That's the starting point. Then where was he at 2.5 seconds? Well, he was at 10 meters. So 2.5 is between 2 and 3. So between here, he was at 10 meters. There's the line. 10 meters would be that point there. And then at 4.5 seconds, he reached 20 meters. So 4.5 is between 4 and 5, so halfway. He was at 20 meters. This line here. There. And once again, take your ruler and a different color pen. And let's join the line. There we are. Excellent. So that's the graph that Harry should have drawn. Let's go for the question. What was Harry's time at 15 meters? So it's given us the distance, we need to find the time. So let's take our ruler again. At 15, there's the line there. We can look across until we touch the line. And then we see what time he got. 15 meters. So, So it seems that at 3.5 seconds, he had traveled 15 meters. So 3.5 seconds. If Harry would have kept running at a constant speed, how long would it take him to reach 25 meters? So suppose Harry likes to run. He wants to reach 25. So here we have 25 is just there. And we look down. There we are. So it seems that it would have taken him 5.5 seconds. So we have here 5.5 seconds. Good. Let's look at the next graph.